Welcome back to the deep dive. When we talk about electrification, the focus is usually on things like efficiency and range.
Right. Passenger cars, delivery vans.
Exactly. But today, we're taking a look at a vehicle where the engineering challenge is far more visceral, far more demanding, and ultimately far more dangerous if you get it wrong.
We're talking about the heavy-duty hybrids cement mixer truck.
It sounds so specific, but the challenge is immense.
It's the ultimate engineering stress test. I mean, this isn't just about moving people or packages.
No.
It's about mobilizing a massive high-inertia load, the concrete drum, and keeping it spinning for hours in really the harshest environments imaginable.
So what's the architecture we're looking at?
It's a P2 hybrid system, but it's paired with a dedicated electric power takeoff, or ePTO. So it's a dual-purpose system that requires, well, a bulletproof design.
And we've been completely immersed in a fascinating document for this. It's a comprehensive engineering white paper.
Yeah, more like a complete capability blueprint. It was put together by a chief HV system architect.
And what's interesting is that this paper wasn't meant to just tweak an existing design. It was written to guide an engineering team on building the high-voltage system from scratch.
Specifically the control logic and, critically, the contactor selection.
That rigorous, almost consultancy-style approach is what makes this source material so compelling.
It is. The entire HV system's success, its safety, its ability to meet these incredibly demanding regulatory standards, it all hinges on one component that is so often just taken for granted.
A high-voltage contactor.
Exactly. And the paper defines its role perfectly. It says it is not a commodity switch. It is the last line of defense in the entire high-voltage safety architecture.
And that phrase, last line of defense, that really sets the stage, doesn't it?
It really does.
Because if you miscalculate the physical limits of this component, or if the control logic around it fails, every other layered safety measure, the advanced software and the battery management system, the fault detection in the inverters, all of that is instantly rendered useless.
Essentially, yeah. If the contactor welds shut during an emergency shutdown, the battery remains physically connected to the bus, and you have a lethal situation on your hands. It doesn't matter how smart your software is at that point.
Okay, let's unpack this. Our mission today is to analyze the mandatory specifications required not just for power and economy, but for meeting the highest possible functional safety integrity level, that's ASIL D, in the face of just extreme electrical, thermal, and mechanical stress.
The operating environment of a cement mixer truck is brutal, and the engineering capability required to handle it is, frankly, staggering.
So let's begin by grounding ourselves in the system overview, the platform constraints. What kind of power architecture are we actually dealing with on this heavy-duty hybrid vehicle?
So we are working within a pretty standard, mature, high-voltage platform for commercial vehicles. It's 400 volts DC nominal.
Okay, pretty standard.
But, and this is critical, the operating range swings wildly. You're looking at a low of 250 volts DC up to a maximum of 450 volts. Control is handled by the standard 24-volt DC low-voltage system you see across heavy trucking.
And that 400-volt standard, I mean, it's chosen for its balance of efficiency and manageability, but it's still highly lethal voltage.
Absolutely.
Now, let's talk about the loads, because this is where the complexity really starts to kick in. We have two primary high-voltage drains.
You do. First, you have the traction motor, which, given the weight of a fully loaded cement truck, needs these tremendous bursts of instantaneous power just to get the thing moving. That's a classic high-peak load.
Right.
But the one that really dictates the contactor design, the one that causes all the problems, is the second load, the mixer drum inverter, the ePTO.
And the ePTO load is continuous.
It is, and that's the key. The source material emphasizes this is a long-duration continuous load. To keep the concrete from setting, to handle continuous mixing on-site, the ePTO can draw a massive 100-kilowatt steady state.
100 kilowatt.
For hours on end. That is like continuously powering about 1,000 standard household light bulbs just to keep that drum rotating. That continuous thermal and electrical draw puts a really unique kind of stress on the contactor.
And the blueprint, it identifies three unique stress factors specific to cement mixers that push the engineering requirements way higher than, say, even a high-powered delivery van.
Yeah, they're pretty brutal.
Let's start with the first one, electrical stress tied to the load profile.
This is defined by what the paper calls the side-by-side driving and mixing scenario. This is common, you see it all the time. The driver keeps the drum rotating while driving through traffic or navigating a construction site.
So combined load.
It's a perfect storm. You
Yeah.
have high DC current flowing to both traction motor and the drum, but you also have high ripple current.
Could you just elaborate on ripple current for a moment? Why does mixing create ripple?
Sure, think of ripple as electrical noise that's superimposed on that smooth DC power flow. Inverters work by rapidly switching the DC current to create the AC needed to drive the motors.
Right.
So when those motors, especially the mixer drum, are running under a dynamic variable load, that heavy concrete is constantly shifting, the inverter's switching introduces these oscillations, or ripple, back onto the DC bus. It's a very, very choppy power draw.
And the physical consequence of that choppy, continuous flow on the contactor itself.
Well, the continuous high DC current leads directly to contact thermal aging. The contacts get hot and degrade, but the ripple current makes it worse by causing what's called magnetic holding decay.
Okay, what's that?
The constant high-frequency oscillations can interfere with the contactor's internal electromagnet, the coil that holds it shut. Over time, it weakens the force holding the contacts reliably closed. This makes the system vulnerable to vibration, and ultimately it shortens its life.
That brings us neatly to the second unique factor, thermal stress. And this happens mostly during that idling for long periods of mixing phase. We've all seen these trucks just sitting still on a job site for half a day.
Yeah, and that idling period is an insidious threat. The current flow isn't necessarily peak traction current, but it is medium to high continuous current just to run the ePTO.
And unlike a passenger car, where high current is usually transient, you accelerate, you brake here, that current can be sustained for 4, 6, maybe 8 hours straight.
Exactly. And all that continuous operation causes heat to just accumulate, with very little cooling airflow because the truck's not moving.
Right, the PDU is just baking.
Precisely. This continuous flow causes significant coil heating within the contactor's electromagnet. And sustained heat, especially above the rated temperature limits, causes spring fatigue.
And the mechanism that opens and closes it.
The very one. If that spring force fatigues, the resistance across the contacts actually increases, which generates even more heat. It's a classic thermal runaway risk. The paper singles this out as the most serious thermal accumulation stress. It's a killer.
Finally, we face mechanical and operational stress, which is really about how the vehicle is used day to day.
This has two major elements. First, the sheer frequency of high-voltage key-on-off cycles. Drivers are constantly starting, repositioning, and shutting down the HV system.
And every single one of those startups requires a pre-charge cycle.
So you have a high pre-charge frequency.
Why is that a stressor specifically?
Because every pre-charge involves routing high voltage through a current-limiting resistor and then immediately closing the main contactor. Even though the pre-charge limits the big inrush, that contact closure, potentially up to 50,000 times over the vehicle's life, causes microscopic contact erosion. And that increases the long-term risk of welding shut.
And then there's just the construction site environment itself. High vibration, lots of dust.
Oh, it's brutal. Think about the constant bone-jarring vibration of a truck traversing an unpaved worksite. The report points out that this environment specifically risks what they call auxiliary contact misjudgment.
What are auxiliary contacts?
They're little low-current switches that report the contactor's mechanical state back to the vehicle control unit. If severe vibration causes momentary bouncing or misalignment, we call it chatter, the VCU gets faulty feedback.
Which could lead to what?
A catastrophe. It could mask a true failure, or conversely, it could cause an unnecessary shutdown of the entire system because the VCU thinks a contactor is welded when it isn't.
That detail about auxiliary contacts shows just how intertwined the mechanical design is with the electrical safety logic.
Absolutely.
So let's look at the architectural mandates that come from these extreme conditions, focusing on the power distribution unit, or PDU.
The standard PDU structure is mandatory here. It connects the HV battery pack using 3 specific components. The main positive, which is K plus SAV, the main negative, K, and the pre-charge contactor, K pre.
And the core engineering principle behind this setup is non-negotiable, right?
Absolutely not. The foundational safety principle is redundancy. The blueprint mandates that the main positive and negative paths must be independently controlled. This explicitly prohibits using a single big contactor to break both lines.
Why is that so important?
Because if the positive contactor welds shut, the negative one must still be able to open and break the circuit, and vice versa. It's an immediate physical safeguard against a single point of failure.
And the pre-charge contactor, K pre.
It has to be in parallel with the main positive contactor, K plus secondary. This structured separation ensures that the main contactor only closes after the capacitors are safely charged, which protects the contacts from that devastating initial current spike. This PDU topology is really the physical manifestation of the ASIL D safety strategy.
We've established that the contactor is the last line of defense. This brings us directly to functional safety, IC 26262, and the maximum rating,
ASIL D.
the highest level. It's easy to say ASIL D, but we need to understand why this specific component demands that highest possible integrity level.
It all comes out of the Hazard Analysis and Risk Assessment, the HARA. When you analyze the core hazards, the worst-case scenario is crystal clear. The contactor fails to open, it welds, or it sticks shut. If that happens, the vehicle is electrically uncontrollable.
And the result of that failure is peg at the highest risk level. Let's break down the three factors that define ASIL D. Severity, S, exposure, E, and controllability, C. Starting with severity, S3.
S3 means severe consequences. We're talking potential for death or a major vehicle fire. If the contactor welds shut during a crash, that battery is still pumping lethal high voltage onto the vehicle chassis. The severity cannot be higher.
Next up is exposure, E3.
E3 means high exposure. The truck operates constantly, daily, for hours on end, across its entire life. So the high voltage power-on condition where the hazard could occur exists throughout nearly the entire operational life cycle. It's not a rare event, it's continuous.
And maybe the most critical factor, controllability, C3. If the driver or a first responder can't easily mitigate the hazard, that's C3.
Exactly. If the contactor is physically welded, there is nothing the driver or a rescue team can do with normal controls. Turning the key, hitting an e-stop button, none of that will interrupt the circuit. It requires specialized tools and risky physical intervention, making the fault basically impossible to control in an emergency.
So you combine S3, E3, and C3.
And ASIL D is the only possible conclusion. It's inescapable.
I think that really clarifies the high stakes. So this ASIL D rating, it isn't a recommendation, it's an absolute mandate. What three concrete design pillars flow directly from this?
The blueprint demands three non-negotiable safeguards. First, a redundant disconnection path. This is why we must have independently controlled K plus and K contactors. If K plus welds, K must still be able to open the circuit.
Okay, second.
Independent diagnosis monitoring. You can't just rely on a best guess or simple current sensing. You need high-precision weld detection that operates independently of the command you send to the coil.
So how do you do that?
Usually with voltage sensors monitoring the bus or those auxiliary contacts we mentioned, providing real-time mechanical feedback. ASIL D requires extremely high diagnostic coverage, like 99%. You can't get that without redundant independent sensing.
And the third pillar is just brute force, physical capability margin.
That's it. It means the contactor has to be physically and electrically strong enough to just withstand the worst-case scenario. Its braking capacity has to exceed the maximum short-circuit current the battery can deliver. We're designing it not just to interrupt current, but to withstand physical forces trying to tear it apart.
Moving from internal safety to external requirements, the system has to comply with global regulations, all of which enforce the famous 5-second rule.
Yeah, this is standardized everywhere. ECE R100 in Europe, FMVSS 305 in the US, GB 12384 in China, they all agree. In any safety-critical event, a crash, a shutdown, an interlock disconnection, the high-voltage bus voltage has to discharge to below 60 volts DC within 5 seconds.
Why is 60 volts DC the magic number?
It's the globally accepted standard for being safe to touch. Below 60 V, the risk of lethal shock is considered very low. And getting there in 5 seconds is easy in theory, but brutal in practice for this trek.
I can imagine. I mean, you open the contactors, the battery's isolated. Shouldn't the voltage just decay on its own?
That's the critical misconception. Opening K plus and K isolates the battery, sure, but the energy remains stored in the downstream DC link capacitors. For a 100 kilowatt mixer system, that capacitor bank is massive. The source material estimates around 3,000 microfarads.
That's a huge amount of stored energy.
It is. It's latent energy that needs to go somewhere.
So just passively waiting for it to bleed off isn't fast enough.
Not even close. If you wait for a passive bleed, you might hit 60 volts in 30 seconds, maybe a minute. You have 5. This mandates an active solution.
What does that look like?
It requires an active discharge circuit, a dedicated power resistor, and a switch that's immediately triggered on crash detection. This circuit has to rapidly burn off all that stored energy to get the bus voltage below the safe limit inside that regulatory window.
Okay, finally, let's talk about the environment's impact on insulation and dielectric requirements. Given the 450 Vmax, What are the testing baselines?
Electrically, every HV component has to withstand a high potential test, 1800 volts AC for 60 seconds. That ensures robust insulation. For resistance, the regulatory minimum is over 100 ohms per volt, which is about 40 kiloohms for a 400 volt system.
But the engineering team here is being pushed to go way above that minimum.
Absolutely. The blueprint rejects minimum compliance. Good engineering practice, especially for a truck with a 15-year life, is to build in a massive safety margin. They're aiming for over 200 kiloohms, maybe even 500 ohms per volt.
And what about the physical separation of conductors, the creepage distance? It has to account for the reality of the construction site.
This is where the concrete dust becomes a villain. Creepage distance is the shortest path between two conductors along the surface of an insulator. Construction sites mean dust, humidity, grime. The design has to account for pollution degree 3.
Which assumes what?
Severe conductive contamination. If the creepage distance is too small, that layer of dust, when it gets a little wet, becomes a short-circuit path. Everything has to be designed to withstand literal grit and grime without arcing. It's a key factor in long-term reliability.
We've established the safety mandates. Now let's drill down into the sheer physical challenge of carrying and interrupting this immense power. As the blueprint states, contactor selection has to be based on the most severe operating conditions.
That's right. We're not sizing for average use. We're sizing for the edge cases that cause catastrophic failure. Starting with the basics. Rated voltage. To provide that safety margin over the 450 volt max, the contactor must be rated for at least 500 to 600 volts DC.
And continuous current. This has to handle that long-duration mixing load.
Given the 100 kilowatts steady-state draw and accounting for losses, the main contactors need a continuous current capability of 400 to 600 amps. But, and this is critical, that rating has to hold true at a sustained high ambient temperature, specifically 85 degrees Celsius.
So that thermal derating is essential.
It is. If you use a contactor rated 400A at room temperature, it might only handle 250A at the real operating temperature before it overheats and fails. The thermal stability is just as important as the current capability.
Okay, now let's discuss the short-term peak demand, the peak load and breakaway torque.
This is where the physics of concrete, a non-Newtonian fluid, kicks in. It gets thicker, thixotropic when it's standing still.
Like a jar of ketchup that's sat for a while. You have to smack it to get it to flow.
It's a great analogy. When the concrete is static, it requires a huge amount of force breakaway torque to get that drum moving again. This translates into a massive, instantaneous surge of current to the mixer drum motor.
And how does the contactor handle that huge spike?
The spec mandates an overload capability of 600 amps for 1 minute.
For a full minute, that's not just a spike.
Exactly. This minute-long requirement covers what engineers call inching operations, frequent short movements of the drum or trying to start a completely stuck load. The contactor has to endure this severe thermal pulse without welding.
Now for the absolute heart of the challenge, the physics of inductive load breaking. A motor is highly inductive. If you try to interrupt current flow to it, it fights back.
It creates a fierce electric arc. When the contacts open, the motor's self-inductance resists the sudden drop in current, generating a huge back EMF, a kickback voltage. The resulting arc voltage is the system voltage plus that inductive spike.
And that kickback voltage is where the energy is focused, vaporizing the contact material.
Correct. For these large drum motors, the L over R time, constant how long the magnetic field takes to collapse, is significant. That means the arc is sustained and incredibly energetic. If the contactor isn't designed to quench that arc rapidly, its electrical life just drops through the floor.
So we can't just take a contactor designed for resistive loads like battery charging and assume it works for the motor.
Absolutely not. The selection rule is a hard derating factor. Contactor ratings for resistive loads have to be derated by a minimum of 40 to 60% when you apply them to high inductive loads like this motor.
How do you make sure the derating is accurate?
You demand data. The engineering team has to get statistical lifetime data from the supplier, the DC inductive load B10, B50 life data.
What exactly does B10, B50 tell an engineer?
It's a critical reliability metric. B50 is the point where 50% of the tested components have failed. B10 is the point where only 10% have failed.
So for an ASIL D component, you're not designing for the average life.
No, you're aiming for an extremely low failure rate. B10 becomes crucial. This data is the hard proof that the arc quenching mechanism works under these specific inductive conditions.
That attention to statistical failure is a hallmark of ASIL D design. Now let's talk about the catastrophic failure scenario, the
hmm
short circuit, and the physics of levitation.
This is a spectacular mechanical failure mode that few outside of high-power engineering ever consider. When a massive short-circuit current occurs, we're talking up to 6,000 amps on this bus, it generates an immense, instantaneous electromagnetic repulsive force, the home force.
How immense is that force?
It's enough to physically push the contacts apart, even though they're held closed by a powerful spring and a magnetic field. We call this separation levitation. And it happens in the critical window 10 to 30 milliseconds before the main fuse physically melts.
Wait, if the contacts levitate, that seems like a good thing. The circuit opens?
It's the worst possible thing. When they levitate, even by a tiny bit, a micro arc forms between them, and it's an arc carrying 6,000 amps. This vaporizes the contact material, creating a molten surface.
And then?
When the home force disappears because the fuse has finally blown, the contacts slam back together due to the spring force. But now their surfaces are molten and pitted, and they are incredibly prone to permanent welding.
So the very force that tries to open the circuit inadvertently creates the perfect condition for it to weld shut forever. That's astonishing.
It's a profound design challenge. The structural and magnetic design has to actively resist this repulsive force. The mandatory spec says the contactor must withstand 6,000 amps for 20 milliseconds without contact separation or explosion. It has to hold fast long enough for the fuse to do its job.
It's clear that traditional components just won't survive these physics. Section 4 of the blueprint lays out the mandatory technology choices. And before we even get to the main contactor, we have to go back to the pre-charged circuit design.
The pre-charge function is non-negotiable. Its whole purpose is to safely charge that huge DC link capacitor bank through a current-limiting resistor before the main contactor closes. This manages the inrush current, preventing the spike that would guarantee welding.
Let's focus on the component that absorbs all that punishment, the resistor. We said the capacitance is about 3,000 microfarads and the max voltage is 450 V. You calculated the energy per pulse.
The calculation is E equals 1/2 CV squared, which works out to approximately 304 joules that have to be instantaneously absorbed by that one resistor.
Every single time the driver keys on the HV system.
Every single time.
That's like a micro explosion of thermal energy every few minutes on a busy construction day. That energy pulse is significant.
And this is where component choice becomes safety critical. The paper explicitly warns, standard wire-wound power resistors cannot handle this. They would burn out or drift in value after only a few hundred cycles.
So what's the mandate?
The design must use ceramic composition resistors. These are specifically engineered to handle immense short-duration thermal pulses. The specification requires a single pulse withstand capacity of over 1,000 joules.
1,000 joules. That's a margin of more than 3 times the required energy.
Exactly. It's there solely because of the duty cycle of a cement mixer driver to guarantee the safety function remains operational for the full vehicle life.
That's incredible. And what determines when the pre-charge phase is successful?
The logic threshold is strict. Pre-charge is complete when the HV bus voltage reaches 90 to 95% of the battery voltage. Failure to reach this percentage within the specified time, say 300 to 800 milliseconds, has to register an immediate fault and prohibit the main contactor from closing.
Moving to the main contactor technology, the blueprint identifies 2 mandatory interconnected technologies. First, sealing technology, ceramic-brazed sealing.
This is a fundamental decision on reliability. Cheaper options like epoxy seals are rejected. Ceramic brazing involves welding ceramic insulator pieces directly to the metal housing. This gives you superior gas tightness,
Which is important for what?
preventing the leakage of the internal arc-quenching atmosphere over the vehicle's life. Plus, the vibration resistance is phenomenal, and it provides higher thermal stability. Ceramic brazed seals maintain integrity at temperatures over 175 Celsius, where epoxy seals start to degrade around 125.
And the second mandatory technology is directly linked to the first, the arc-quenching gas. They have to use hydrogen or a mixture.
This choice is driven entirely by the need to safely interrupt that high DC inductive current. When you open the contactor, a fierce arc forms. You need a gas that can cool and extinguish that plasma rapidly.
And hydrogen is the best for that.
It's the gold standard. It has 7 times the thermal conductivity of nitrogen.
7 times. That's a massive difference.
It allows the contactor to rapidly cool the electric arc, draining its energy and accelerating the interruption. This dramatically reduces contact erosion. The analysis found that nitrogen is just insufficient for the life cycle required here.
And you need the ceramic seal to keep the tiny hydrogen molecules from leaking out.
One technology mandates the other.
We've built up a huge list of requirements. To wrap this up, let's review the key figures on the final specifications checklist.
We're looking at a system rated for over 500 volts DC, capable of over 400 amps continuous at high temperature. The structural design has to survive a short-circuit current of over 6,000 amps for 20 milliseconds without levitation.
And the life cycle demands are tough. An inductive brake capacity of at least 600 amps at 450 volts for 10 cycles, and a total mechanical life of over 1 million cycles.
Plus, the physical toughness. Vibration tolerance of 20 gram sine and shock tolerance of 50 GeV. These are specifications you'd normally see for aerospace components, not construction trucks. These are the numbers that guarantee ASIL D safety.
The physical component is only half the battle. Now we have to turn to the brains of the operation, the control logic and safety state machine. This has to be designed for ASIL D, meaning it must operate with zero chance of an undetected failure.
Right. The state machine replaces simple on-off-F logic with a closed-loop diagnostic process. It governs every single power-up and shutdown sequence, ensuring safety checks are performed at every single step.
Okay, walk us through the power-up sequence, starting with initialization.
State 1, init. The VCU and BMS perform initial self-diagnostics. Critically, they confirm the HVIL, the high-voltage interlock loop, is closed, guaranteeing all the HV connectors are properly seated.
Then, the critical pre-start diagnosis, the weld check.
State 2, weld check. This is a mandatory safety gate. With all contactors commanded to be open, the system reads the voltage on the downstream HV link. If that voltage is above the 60-volt safety threshold,
It means something is stuck closed.
it means a contactor is physically welded. This is immediately flagged as an ASIL default, and the sequence just halts. You can't start if the system is already unsafe.
Assuming the coast is clear, we start closing components.
State 3, close curfew, main negative. The negative line closes first. Then state 4, close curfew, pre-charge. This engages that big ceramic resistor circuit we just discussed.
And this step requires intense monitoring, right? We're watching that voltage rise.
Precisely. The system monitors the voltage rise over time. The expected pre-charge time is tightly controlled, generally 300 to 800 milliseconds. If the VCU detects a timeout, say over 1,000 milliseconds, or if the voltage fails to reach that 95% threshold, that's a pre-charge failure. It faults and aborts.
And if the pre-charge is successful,
The gates open, state 5. Close K+, main positive. This is only permitted after successful pre-charge confirmation. Once K+ is closed and conducting, state 6. Open K-pre. The pre-charge contactor is released. And then, state 7. System ready.
that choreography is so detailed. But how does the system maintain continuous safety monitoring after startup? We need that double verification weld detection strategy.
Continuous detection requires two independent methods to achieve ASIL D's high diagnostic coverage. Method 1 is the auxiliary contact method, or mirror contact. This is mechanical feedback.
How does the mirror contact work?
The auxiliary contact is mechanically linked to the main ones. The system continuously compares the coil drive signal, the intended state, against the auxiliary contact feedback, the actual physical state. If the coil is commanded open but the auxiliary contact reports closed, you have definite proof of a weld.
And the second method covers scenarios where the auxiliary contact itself might fail.
That's where the voltage profile method comes in. When the VCU commands K+ to open, it monitors the resulting voltage decay on the HV bus. If K+ opens, the voltage should drop rapidly. If the voltage just sits there, it proves K+ is stuck. This dual verification loop is the core of ASIL D integrity.
And the consequence of a failure detection.
The paper is clear. The system must prohibit any immediate subsequent power-up attempts. You can't just let the driver cycle the key until the fault is physically cleared.
Let's discuss the end of operation logic, shutdown and emergency logic. There's a big difference between a normal shutdown and an emergency one.
In a normal shutdown, the goal is contactor longevity. You minimize the current being broken. The sequence is: first, command the loads to shut down, reducing current to near zero. Then open K+. Finally, open KES. This prevents the high energy arc and extends the contactor's life.
But in an emergency shutdown e-stop, crash, a severe fault.
Speed and redundancy are everything. The blueprint mandates instantaneous, simultaneous action. Simultaneously open K+ and K, the ASIL D path, and immediately trigger the independent PDU active discharge circuit. This guarantees you meet that critical 5-second sub-60 volt requirement.
Now for the final piece of the control logic puzzle. 24V coil PWM energy saving control. This seems like a small detail, but it addresses that thermal stress we identified.
It directly combats that thermal accumulation during long mixing periods. When the truck is idling, the contactor coil is constantly energized, drawing power and radiating heat. PWM control maintains closure with minimal power.
So how does it operate dynamically?
It's a two-phase process. The initial pull-in phase, for about 20 to 200 milliseconds, uses a 100% duty cycle. This gives you maximum magnetic force to guarantee a clean, fast closure.
But once it's closed, you can back off the power.
Exactly. You switch to the hold phase, using PWM at a much reduced duty cycle, 20 to 50%. This maintains closure, but achieves a significant 30 to 50% reduction in coil temperature. This seemingly minor efficiency gain is critical for the longevity of all the surrounding components in that hot PDU.
A blueprint is just paper until it's validated. The engineering required to define the components is matched only by the rigor required to prove they can withstand this life. Let's look at mechanical and environmental durability.
The standards for this are brutal. The testing has to use the extreme ISO 16750-3 commercial vehicle frame-mounted spectrum. This isn't just shaking apart. This is sustained random vibration testing where acceleration levels can reach 5 to 10 RMS for dozens of hours per axis. It simulates years of road shock in days.
And during that severe vibration, we have that micro-level requirement, contact chatter.
This is the moment-to-moment test of integrity. Under max vibration, the contacts must not bounce when closed. The paper sets an extremely stringent limit. Contact chatter must not exceed 10 microseconds. Anything longer is treated as a potential fault.
And the environmental protection needs to withstand the cleanup crew as much as the grime.
Precisely. The PDU has to meet IP67, IP6K9K. IP67 is for submersion. IP6K9K is the crucial one. It's the ability to withstand high-pressure, high-temperature water jet spray. These trucks are aggressively power washed daily. If the PDU sealing fails, the internal components will corrode and fail.
Let's turn to the electrical tests. How do they validate the component against the specific demands of the inductive load over its lifespan?
They conduct electrical endurance testing that simulates the real world. The plan mandates 10,000 cycles of on-off switching running at 400 volts and 300 amps with a 50 microhenry inductor intentionally placed in series to mimic the motor.
And that pre-charge circuit requires its own endurance marathon.
It does. That 1,000 joule ceramic resistor needs its reliability proven. The spec demands 50,000 pre-charge cycles, simulating frequent key-on-off events. During this test, they monitor the component for resistance drift. It has to stay within a 5% margin.
Finally, the ultimate stress test, destructive testing. You have to prove the fail-safe nature of the design.
This is a one-time, non-recoverable test. They force the contactor to perform a single guaranteed-to-fail cutoff, interrupting 2,000 amps at 450 volts DC. This simulates an extreme catastrophic failure mode.
What's the success criterion for intentionally breaking something?
It's specific and focused on safety, not survival. The contactor is allowed to fail internally. It will be destroyed, but it must not ignite, explode, or vent flames. It has to maintain its external insulation integrity.
So in a worst-case electrical event, the component fails safely.
It fails in a way that protects the vehicle and the people around it from fire and electrocution. That is the definition of ASIL D hardware integrity.
So what does this all mean for the engineering teams looking at vehicle electrification in the heavy-duty sector? This blueprint is a masterclass in designing for the absolute edge case.
It really is.
It shows that electrifying a cement mixer truck is far, far more complex than electrifying a passenger car.
It's a deep integration problem. The contactor selection here is a beautiful example of how extreme physical limits, like that 6,000 amp short circuit withstand and the 1,000 joule ceramic resistor, have to be meticulously integrated with the highest level of functional safety logic, the ASIL D state machine. You can't compromise on the hardware physics or the control software.
The success of this entire platform, its safety, and its ability to operate reliably on a dusty, vibrating construction site truly hinges on those non-negotiable mandates.
We saw three specific elements that really rose above the rest: the ceramic-brazed sealing for physical robustness, the hydrogen arc quenching for efficient current interruption, and the redundant ASIL D compliant state machine that manages every single check. If you skimp on one, the entire system fails the ASIL D mandate.
I keep coming back to that final detail in the control system. The use of 24-volt PWM to reduce the coil temperature by up to 50% during the holding phase. It's such an optimized solution to a serious thermal problem.
It is, and it raises a fascinating final thought for you to consider. We focus so much on the thermal requirements of the high voltage side, the contacts, the arc quenching. But the coil control relies on sophisticated MOSFETs and controllers operating on the low voltage 24-volt bus.
Right?
The mandate to optimize for efficiency by reducing coil power means the low voltage control circuits now have to precisely manage that PWM holding current without failure, and they're often operating within the same sealed, hot PDU enclosure.
Ah, so they're a heat source too.
Exactly. So given these severe thermal constraints, how much more thermal margin must be engineered into the low voltage control circuits themselves? What unforeseen system-level challenges are created by optimizing the efficiency of the control system when the control system is itself a heat source in that punishing environment? That decision tree never stops branching.